This conference will now be recorded.
So, good evening, all. Today we'll be learning the most interesting part, universal law of gravitation. We had started this chapter in the last class, last Thursday, and we have learned about Kepler's law. So, we'll be deriving Kepler's law after learning this universal law of gravitation. So, today let us see brief history about this law of gravitation, how Sir Isaac Newton was inspired, and how he came to the conclusion or came up with this celebrated law. So, as you can see in this cartoon figure, Sir Isaac Newton in 1665, when he was in the garden, he actually belongs to a royal family, so he was just relaxing in garden. Apple tree was there, and he eventually could notice that an apple falls from the tree. So this clicked into Sir Isaac Newton's mind, that why apple always or anything always falls from top to bottom or towards the earth. Why doesn't it go away from the earth? Okay, why it always falls towards the ground or towards the earth? So this inspired him a lot to find out the reason behind that, and which leads to the discovery of universal law of gravitation. So we'll see what was his initial idea to find out the law of gravitation. As we discussed in the previous class, history about it. So by that time, Sir Isaac Newton was in this condition. Already few things were known, like planetary motion somewhat was known. Planetary motion, like at least Copernicus, then Kepler already had given idea about planetary motion. So there was an idea that the moon revolves around Earth and nearly in the circular orbit. So this is suppose moon and this is Earth. It revolves around Earth. Okay, and he has seen everything, whatever thrown up or naturally falls, like from like apple or maybe any fruit from any elevated position, it always comes to the ground. So his idea was that the force which attracts the apple towards the earth may be same as the force attracting the moon towards earth. So as I said, it was already known that sun revolves around, moon revolves around earth. So he thought that maybe the moon is also attracted by earth, and also anything like here it is apple. also is getting attracted towards the earth. So perhaps the same force is the cause of this attraction. Okay, whether this attractive force is same for both the cases. So with this idea, see what he had done. So moon revolve around the earth in a circular orbit, that was assumption. And we know from our circular motion, that notion, like anything revolves around a circular, like anything moves in a circular path will be acted upon by a force called centripetal force. That means I want to say that circular motion is actually circular motion happens due to centripetal force. And obviously there is opposite force which is called centripetal force. Centripetal force we have already discussed. It always acts towards the center. If your object is here, it will be acting this way. If your object is here, it will be acting this way. If your object is here, so it will be acting this way, like this. So centripetal force in any circular motion is the driving force or responsible for making that body move in that circular path. And we know centripetal force Fc can be given by, suppose this is having mass small m, this object yellow one which is moving, suppose this is moon and this is earth. Okay, and the distance between moon and earth is r. Then centripetal force is actually m c in this. So speed will be in this way, right? Always along the direction tangent to the point. Okay, so at any point the direction of the speed will be linear speed. Okay, direction of the linear speed will be always tangent to the circular path at that particular point. So this is the speed. So if we know the speed, if we know the distance between the earth and the moon, then we can get the centripetal force mv square by r. And one more thing is, if we want to get acceleration, centripetal acceleration, then it will be simply v square by r. Okay, so look, the idea was that whether the same force attract the moon towards the earth which is attracting the apple towards the earth. So if that is the case, then see, we already know few informations about the motion of moon or revolution of moon around the sun, sorry, around the earth. So what we know, we know already by this time Newton knew, like there was data available for the time period of the moon. Okay, this is moon which is revolving around the earth in a circular orbit, nearly circular orbit. This is the rate, the distance between the centers of the earth and the moon. This is earth. Okay, so we know centripetal acceleration will be given by AC is equal to v square by r. Okay, so if we can find out this v square by r, v means speed, linear speed, r is the distance, this one. Okay, now what were known, the time period of revolution of the moon was sorry, this was actually, yes, the time period was known for this orbit. Okay, so moon takes almost how many days, 27.3 days to revolve around the earth. Okay, so if we know that that is the time period, then time period is 27.3 time period of revolution is this much, and if we know this r, so we can find out what is speed. How? 2 pi r, this is the perimeter of the circular path divided by time period. Okay, if we put all these values like 2 3.14, this r is having value 3.84 into 10 to the power 8 meter, and 2 pi r, and in the denominator, this is, if we make it into second, so 24, this is this many days, so one day into this many seconds. So if you just put it, like if you just do this simplification or calculation, what you get is 1.02 into 10 to the power 3, 10 to the power 3 meter per second. So we can get the speed. So Newton got the speed. And see, once we get the speed, I'll just write it here directly. I'll just remove all this so that I get space over here. So he got the speed, this. So now putting this speed and the this is the distance between the centers of the earth and the moon. If we just put it there, then see v square means 1.02 into 10 to the power 3 whole square, okay, divided by, this is 3.84 into 10 to the power this much meter. So it will give you meter per second square. So if you just calculate this, you get somewhat like 2.72 into 10 to the power minus 3 meter per second square. So what is the acceleration you get? 2.72 into 10 to the power minus 3 meter per second square. So the idea, what he got, that the force which attracts the apple towards the earth may be of same origin, like which is actually attracting the moon towards the earth also. So I'm just taking, considering the revolution of the moon around the earth, and from there if I get the centripetal acceleration, then that should be equal to, so according to this idea, what Einstein, like Newton, Sir Isaac Newton should get, AC is equal to G. Okay, this centripetal acceleration must be equal to gravitational acceleration, and eventually gravitational acceleration was already known by that time as 9.8 meter per second. Okay, sorry, second square. So this much was already known, but how much you get as AC? See, AC is actually much less than, much less than G. Okay, this is 9.8. Here see, this is the order. Okay, so it is much less than G. Then he thought there may be a mistake. So where was the mistake? Let us find out. And if see, he thought the force must be depending on the distance. Force must be depending on the distance. So I'll just write it here briefly. So from this idea, he got AC much less than G. Okay, then what modification he was, like he thought, he was thinking, modification is that force must be force must be or acceleration must be force or acceleration in both cases in the sense when the apple is attracted by earth or the moon is attracted by the earth, in both cases the force or the acceleration must be depending on the distance, depending on the distance from the center of the earth. Okay, so see, apple is actually very near to the earth's surface, or towards the center it has. Okay, so it is actually at very less distance maybe, but the moon is maybe at greater distance. That's why the acceleration, centripetal acceleration, becomes very big, like was calculated to be very less than g. So now what he had thought, let us see this one. So he argued centripetal acceleration or gravitational acceleration both must be varying as the square of the, like inverse, square of the inverse of the distance between the particular object and the center of the earth. So this might be the case. Okay, or this. Okay, look, then what he had done, he had he had thought then this may be directly proportional to this, like inverse square dependence, and g also must be having inverse square dependence of this earth, because this is g is actually on the earth surface, we are just seeing on the earth surface, and this is centripetal acceleration for the moon. Okay, this is r. All right, so he had thought to take, the ratio and see what happens. So this will give you r square divided by r, r e square divided by r. So I can write it re by r, this, and this actually re by r was also known as 1 over 60. So if you just put this value over here, look what you get is AC is equal to G into 1 over 3. So yes, RE by R. So you get G into this over 1 over this. So if you just make it like this, see, you get 9.8 into 1 over this, which actually gives you nearly 2.72 into 10 to the power. This gives like this, 10 to the power minus 3 meter per second square. So this is the thing you get. That means this inverse square law is actually satisfying the criteria. Okay. So from this idea, he could arrive to this inverse square distance dependence of the force. Inverse square dependence of the force, gravitational force. So this is how he arrived to the universal law of gravitation. And what is the statement for that? Every particle in the universe attracts every other particle with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And these forces act along the line of the joining. So here I have taken two masses, suppose M1 and M2. Okay, M1 and M2, and they are separated by a distance small r. Okay, now according to the universal law of gravitation, suppose I write Fg, the gravitational force, which is directly proportional to the product of the masses. Okay, and second thing is it is inversely, it is proportional to inversely, like proportional to the inverse of the square of the distance between these two particles or those masses. Okay, these are actually, this law was first derived for point masses. And see, if we combine these two, so gravitational force is directly proportional to the product of the masses, and it is inversely proportional to the square of the distance between the two masses. Now if we combine these two, then we get Fg is equal to G into m1 m2 by r square. Okay, and this force is attractive in nature. That means if you see, if I say the force, see, if I say this is m1, suppose this is the force on f1 due to 2, and this is the force on f2 due to 1. Okay, these two forces are actually, they are attracting each other, they attract each other. Like see, the earth is actually attracting the apple towards the center. That's why it is falling. Or in that case, any object, if you just leave in the air, that will come to automatically to the ground. This is due to this gravitational attraction by the earth. Okay, so I have taken any arbitrary two objects, to any arbitrary objects m1 and m2, having masses m1 and m2, and they are situated at r distance apart, small r distance apart. So in that case, the force is C, G is equal to like Fg is equal to G into m1 m2 by r square. This is the magnitude of the force. Okay, magnitude of the force. And see, since it is an attractive force, so this can be written as minus G m1 m2 by r square. This is the real form or the original form of the gravitational, like the or mathematical form of the universal law of gravitation. Okay, this is what generally we know. And see, this is G, this capital G is called universal gravitational constant. Universal gravitational constant. So what is that? G is called universal gravitational constant. Universal gravitational constant. Okay, gravitational. Uh, this is the universal gravitational constant. And see, this constant is is having a dimension. It is not a dimensionless quantity. It has certain dimension. We will be able to find that dimension. Let us find that dimension. See, we have got the force already, equation of the force. See, as I was just mentioning, this force is attractive force. Suppose I write this F1 to, this is the force F1 to force on M1 due to M2. Okay, or this is F21 is force on M2 due to M1. Okay, due to M1. So these two forces are, you look, the force F1 to, the force exerted by the mass 2 on M1 is actually towards itself. So if I say this is the radius vector, so the force is actually always, force is always in the opposite direction of the radius vector. In the opposite direction of the radius vector. Okay, so this is why there is a minus sign. Okay, so this is actually attractive force. Now let us find out the dimension and unit of this gravitational constant. So as you can see from here that we'll take the magnitude of the gravitational force, that is G m m1 m2 by r square. Let us take this magnitude itself. So if you just find out what is force into meter square, this is the distance square, this is m1 and m2. So you get this is Newton and this is meter square, and look, this is having kilogram, so kg square of kg square. So you get Newton meter square per kilogram square. Okay, this will be the unit of the gravitational constant. Okay, and it has a specific value. You can see sometime in the board exam and all, dimension of this gravitational constant also can be asked to find out. So if we write this Fg is equal to G m1 m2 by r square, let us find out the dimension from this equation itself. So this is having the dimension of force into dimension of the square of the distance, and these are the two masses. Okay, dimension of these two masses. So you look from here also, you can find out the unit. So here force is ml t to the power minus 2. Okay, this is the dimension of force, and then it has dimension of length square l square, and divided by this is mass square. Okay, if you do the simplification, then you look the dimension of this G universal gravitational constant will be par, this is, okay, this is here, then L cube t to the power minus 2. Okay, so m to the power minus 1, L to the power 3, and t to the power minus 2. So this will be the dimension of G. Okay, and this G has a value. We'll write the value in SI unit. It has no need to remember this, but it will be good if someone can remember the value. But nowadays in any competitive exam the value will be given 6.67 into 10 to the power minus 11 Newton meter square kg to the power minus 2. Newton into meter square kg to the power minus 2. So this is the value 6.67. 6.67 into 10 to the power minus 11 Newton meter square per kg square. Okay, so this is universal gravitational constant, and we have learned what is the gravitational force. Mathematically it is given minus G m1 m2 by r square. So this is the force. Okay, now we'll see, we have already learned the equation of the force. Okay, so one more thing I have to do here. So how do you get the definition of G? So definition of G can be obtained, see, from here, F into Fg into r square by m1 into m2. Okay, so from here, if the two masses, suppose if I define this G in SI unit, so suppose m1 is m1 m2 both are 1 kg, and they are separated by 1 meter distance. Then the force, so this is also 1, these two are also 1, then the force exerted by one body to another will be equal to gravitational constant. The universal gravitational constant may be defined as the force of attraction between two bodies of unit masses each and placed at unit distance apart. All right. So the universal gravitational constant defined as the defined as the force of attraction between two unit masses when they are unit distance unit distance apart from each other. They are at unit distance apart. Okay. So this is the definition of universal gravitational constant. So universal gravitational constant may be defined as the force of attraction between unit masses two unit masses when they are at unit distance apart from each other. Okay. So this is the definition of universal gravitational constant. Now there are few important features of gravitational force. Important features means like in what condition the force may be applied and what are the conditions where like what are all characteristics of this gravitational force. So those are actually known as features. So the gravitational force between 2 point masses is independent of the intervening medium. That means if you have two objects inside the water, okay, suppose M1 and M2, they are they are kept r distance apart inside the water. The gravitational force, suppose FGW, and if they are brought up in the air and kept at the same distance apart and found out the gravitational force or attraction between them in air, the two forces will be equal in magnitude ideally. That means it does not depend on the intervening medium, whether there is air, there is water, or any other medium. Okay, it does not depend on what medium is there in between the point masses. Okay, so gravitational gravitational force obeys Newton's third law. As I was saying that if there are two objects, so this is M1, M2, so the force on 1 due to 2 and the force on 2 due to 1, they are, look, this is F21 and this is F12. So these two are, since the distance is constant and also the force, actually the magnitude of these two forces will be equal. Okay, but they act in the opposite direction. That means these two forces actually form the action and reaction couple. Okay, kind of that. So this forms action and reaction. If one two is action, then the other one will be reaction. So that's how we can write this as F12 is equal to F21. So this attraction between two gravitational attraction between two objects or 2 point masses form an action and reaction pair. Okay. All right. So if I just say in very simple word, each object will be the attraction. See, the force of attraction by each object will be the same and in the opposite direction. Suppose I take a very big mass and a small mass. Okay. So look, they are distance apart. So the force, suppose this is a Fm, capital M due to small m. This will be in this direction, and if this is the magnitude of the force, in this way also this small object also will experience, like it will also attract the small, see the capital object with the same force. I mean to say the big object attracts the smaller object by applying a force Fm capital M. Okay, and the small object attracts the capital this bigger object with this force, and eventually these two forces are same because they are action and reaction. So magnitude will be the same. Now there is a question. Suppose in this case, Earth and Apple, they are two objects now. So this is my Apple. Okay, the smaller object is Apple. Okay, smaller object is Apple, suppose, and this is the Earth having capital mass. Okay, now these two objects, like Earth is attracting the Apple with suppose 12 Newton force. Okay, 12 Newton force. I'm just taking arbitrarily 12 Newton force with 12 Newton force. That means force force on the small object due to the Earth. Okay, or Apple due to the Earth. So according to this nature, that the gravitational force is a pair of action and reaction. If this force on the Apple is the action by Earth, then Apple also will give equal and opposite reaction, that is the force on the Earth due to Apple will be also the same, having the same magnitude but with a negative sign. That means the Earth is actually attracting the Apple towards itself, its center, whereas the Apple is also attracting the Earth with the same force towards its center. But then why Apple is going towards the center of the Earth? Why this Apple is moving but the Earth is not moving towards the Apple? So this is a wide question. So there will be sometime a viva question that why Earth is not moving towards the Apple whereas the Apple is moving towards the Earth. Why is it so? So motion actually depends. The motion is characterized by velocity or acceleration, right? Acceleration or velocity. Now in this case, force may be the same, but look, Earth has huge mass. So the force may be the same. Suppose same 12 Newton, same 12 Newton, Apple is applying or attracting with this same 12 Newton. But what is the acceleration of the Earth? It has huge mass, capital M. So the attraction of the Apple, like force wise, it is same force with which the Earth is attracting the Apple, but the acceleration which is created in the Earth is very negligible. Whereas the attraction produced in the Apple because of the small mass. See, if I have, see, suppose 12 Newton same force, if it is some billion cases, okay, so it has very big mass, okay, for the Earth, and for this maybe some Apple, maybe some 200 gram or something like that. So it has a finite value. That's why apple actually moves towards the earth center, okay, center of the earth, whereas earth does not move at all because of its huge mass, and acceleration on the earth will be very like of the earth will be very less due to this attraction by the apple. Okay, now another picture is the law will be strictly holding for point masses. See, whatever we see in this universe, everything is actually extended. Like in our real world, whatever we see, those are extended object. That means if I suppose this is a rock or something, so it has a enormous, like it has enormous number of particles, okay, or point masses. Point masses means particle. So there are a large number of particles inside that, or point masses. But here it is saying that this holds good for, or generally strictly hold for point masses. But we see gravitational attraction occurs due like in between massive objects, and see those massive objects are actually composed of very tiny point masses. So in that case, how is it true, or how is it how is it justified to apply the law of gravitation, like universal law of gravitation? We'll see. I'll just take a simple example for this. Like it is applicable for even extended object also. If you take a hollow sphere, if you take a hollow sphere, it has certain mass, suppose m, and you have a point mass small m somewhere here. So if you calculate the attractive force, suppose this is the distance r, attractive force applied by the shell. Spherical shell means empty. Inside there is nothing, no mass, only mass is there just at the surface, spherical surface. So if you calculate the forces by this spherical shell, the force will be such that it depends, like it will be such that the whole mass of this cell is concentrated at the center of the cell. Whole mass, as if the whole mass is concentrated at the center of the cell. Okay, so this is what we can understand, that the extended object also we can just go with center of mass. Okay, or in other words, you look, if we see the vector form of this like a vector form of gravitational universal law of gravitation, then we'll see there may be many particles acting, like having gravitational attraction. Suppose this is a particle for which we have to calculate the total gravitational attraction for. So there are forces like this. So there will be many forces by many other particles. But if we take the resultant of all the forces, then we'll see the force will be actually acting towards a particular direction. Okay, not in all direction. Okay, so it can be applicable well and good for extended object also. That is what I just wanted to mean. Now the gravitational force between two masses is central force, depends only on the distance r. So we have seen that the gravitational force between two objects depends only on the r, not on any angular coordinate like theta or phi. These are the angular coordinate in spherical polar coordinate system. So but we don't see the presence of this theta and phi in the force equation. So that's why the force is always depending on the radial distance. So that's why it is called that the gravitational force has a spherical symmetry. Spherical symmetry. Another point is that since this depends on only on the distance or the along the so force acting always towards a fixed point. Suppose this is there are two masses m1 m2. The force is acting along the line of the joining of the centers, and also it is always directing towards a point. So that's why this kind of forces are called central force in nature. So central force, gravitational force is an example of central force. Okay, and it has a spherical symmetry as it depends only on the radial distance, not on any angular coordinate. It is a conservative force. We know conservative force will actually lead to the storage of potential energy. So we have already discussed this like when you just like lift a book, you are just doing some work. mgh will be, see, if this is the height h, mass of the book is m. If you lift it up to h height, so mgh will be the work done, which will be stored in the object at this particular position as potential energy. So we have seen that gravitational force is central in nature, and also it is a conservative force. In fact, all central forces will be conservative in nature. Conservative in nature. So gravitational force between two bodies independent of the presence of any other third body. That means law of gravitation obeys superposition principle. That means what? You have suppose some 5 objects nearby. So I want to calculate the resultant force on this particular, suppose m1 mass due to all other. Okay, so the force will be acting due to this, due to this, due to this, due to this. Okay, but how to calculate the total force or resultant force acting on this particle? This you have to do the, you have to take the resultant of all the forces, resultant of the all the forces. And one more point you should remember, that when you calculate the force between any 2 points or any 2 objects, then all other objects could be neglected, their presence can be neglected. So that is what it is said, that the force, gravitational force between 2 objects will be independent of the presence of any third object. Okay, this actually leads to the superposition principle. So superposition principle, the same superposition principle what we have already learned in case of electrostatics. Okay, now we'll see the vector form of gravitational force. See, I have got m1 and m2 two forces. So this is taken from NCERT textbooks. So look this, I may also draw it here. This is the coordinate system. As you see, this is x coordinate axis, this is y coordinate axis, and this is the axis of z coordinate. And see, m1 and m2, these two are in the xz plane. Okay, and the position vector of m1 is r1. Okay, this is r1, and the position vector, I'll just write it here maybe for you. So you can see, just a minute. So we know that gravitational force is minus g m1 m2 by r, and this is the radial distance. Okay, so suppose these two masses are not lying in the same line, m1 and m2. So in that case, suppose they are in a same plane, okay, and they have position vectors like this. Okay, so this is r1 position vector, this is r2 position vector. So you have to find out this distance. This is the actually position vector between them. Okay, sorry, not position vector, the distance between them. So if you want to find out this, suppose this is r vector. So this r vector actually can be obtained as, so r, look, this is this way, this is this way, again this is, so r1 plus r is equal to this. So you will get r2 minus r1. This is the vector. Okay, if you take the magnitude, both side you will get the magnitude also. Okay, so this is how. Then for this case, in vector notation, what we have to write, we can write this as r2 minus r1 if you write in this way. Okay, and this will be, see, if I write this as a, okay, let me write it here, f12. So suppose f12, f12 means this, the force exerted by 2 due to 1. So the attractive force will be in this direction. Okay, that means this goes with r, like this unit vector. If I say in this direction, it is r cap. Okay, with a positive sign. Okay, so the force on the object 1 acting in this way. If I just take the force on 2 exit, okay, so let us go with this itself, and the force on the object 2, which is acting in this direction, this is the r2 minus r1, and this will be r21 or negative r. Okay, negative r cap. All right, so this is actually the case, like f21 will be always equal to f12 minus of f12. Okay, so this is the case from here. Now we'll just take up simple example, just 2 minutes, then I'll finish it here. Law of gravitation is actually following superposition principle. We'll just prove it here. Principle. So look, I have three masses of equal, like three equal masses, m1, m2, like a, b, and c at three corner, like three vertices of a particular equilateral triangle, suppose, and the mass of each of them is m. Okay, and I have kept another mass at the center of the triangle, that is 2m over here. So you have to find out the resultant force on this particular object, okay, at the centroid. Okay, okay, so if you want to find out the resultant force, so you look, superposition principle says that if you have these three masses, so suppose, see, in this case I can write the forces on this particular object. Okay, force on, so force which is actually acting due to this a, so force 2m due to small m at a, I'll just write in this, force acting f ga. So this is acting between minus g2m into m divided by this distance I am taking as ga square itself. Okay, ga square. And see, if they are of same length, then we can find out what is this distance. 2 is to 3. So 2 is to 3 of the height. And this will be 1/3 of the height. So we can find it out. No, like it doesn't matter. So but what I need to see is actually the direction. So this force is actually in the j cap direction. So what I mean to say is that if you have many particles, superposition principle is saying that if you want to calculate the force between any two, then you should not be considering at the same time the presence of all others. Okay, you have to neglect the presence of all others. And similarly, when you calculate the force between these two, just neglect the presence of others. Okay, so that's how you have to calculate the force. Suppose in this case I am just calculating, I have to calculate the total force. Okay, so then you can find out, you can just add them up. Okay, so I have got this force on this particle 2m due to the small m. Now I'll just see the force which is g to b. Okay, this is also minus g 2m into m. This factor is all right, always same. This is g b square. And see, this force actually acting in this direction, that means it has two component, one along this, another along this way. Okay, and this angle, if this is an equilateral triangle, this angle will be theta. As you can see, this is theta, means this will be theta. Okay, similar to this, I'll just write it here. If this angle is theta, sorry, theta, if this angle is total 60, that means this will be 30. So if you just draw a parallel line to this BC, this angle will give you 30, as you can see from here also. So this is with the negative x-axis. So there will be, see, this force along BG will be having two components. Okay, one along one along minus I cap direction. Okay, and how much is that? Cos of 30 degree. And another component will be minus this, I can write g 2m into m divided by gb square. This is the magnitude. Along with that, there will be another component this way, that is minus j cap sine 30. Okay, along this. Again, if you just write fgc, similarly you will get that this gc fgc has two component, fgc, one along positive x direction, that is cos 30 degree, positive x direction, and another will be fgc along minus j direction, j cap direction. This is actually sine 30. Okay, so now if you simplify everything, then you look, you don't have any force along this direction, because the resultant will give you like zero force along x direction. Okay, along x direction, whereas you will have certain force along this direction. Okay, y direction. So superposition principle says that when you consider the force between these two, okay, sorry, I have to calculate the force due to all of them over this. So when we consider these two forces, two objects, we don't consider this and this also together. Okay, so we can write down the forces then, or calculate the force in that way. Similarly, when we calculate force between these two, we don't bother the with the presence of this A and C. This is how independently you have to calculate the forces for all the masses on that particular 2m mass. Then once you get f fga plus obviously vector, and then fgb plus fgc, all the forces will give you the resultant force. Okay, obviously this will be the vector sum. So if there are many objects, so if you want to calculate the force on a particular object, that will give you the sum of the resultant, like sum of the forces of individual pair when you neglect the presence of others. You calculate in that way, and then you take the vector sum of all the forces. That's how you'll get the resultant force. So this is actually, this particular problem is given already there in the NCERT textbooks. I just took it to explain you how superposition principle works. Okay, for this gravitational force also. So we have seen in case of electrostatic force, superposition principle was holding good, and in this case also it will hold good. Superposition principle will hold good in this, or in other words, we say universal law of gravitation holds or obeys superposition principle. And we'll see sometime that electrostatic force and gravitational force, they are both actually central in nature, because both are inverse square law. They both have inverse square law, and in the numerator, in this gravitational case m1 m2, in other case it was q1 q2, the charges. Okay, so both are actually central force, and both stores potential energy. So there will be a concept of potential energy whenever there is a force which is central in nature. Okay, so with this I'll stop it here. We'll be learning again very interesting things like gravitational constant, how it varies with distance, how it varies with depth, etc., and how, like, what is geostationary satellite, etc., we'll be learning in the next class. So bye for today.